Hello, I'm Dr. Mark Lewis, and this is a video for my Advanced Algorithms class. We're going to talk about solution spaces and searching those solution spaces. So the problem that I often like to refer to, and I show it to my classes in earlier semesters, is solving a maze. And we simplify this maze by just making it so it's a grid, and every block is either open or it's blocked. This is easier than having some of the edges being solid as you would get in a normal maze, at least as far as how you program it and work with it. So if we had a problem such as finding the shortest path through this maze, we might start here, and if we write this recursively, we wind up checking after this, we check these two locations, and then from each of those, we can check the next set of locations, and from each of those, we can check the next set and the next set. And you can picture the way this works as a tree. So you start at the starting location, and then in this case, there were two squares that we could go to after the starting location. Those two right there. And so I would draw in that I had recursive calls from the starting location to these two, and then say from this one I could have gone, and often when we write this I'd actually branch all four directions and then immediately return from the ones that were invalid, but for the sake of my drawing here I'm only going to draw the fact that I would go to the empty squares. So I have another one here and another one here. And of course, the way the recursive function does this is it actually goes all the way down to the left, depending upon the order in which we did our calls. That would wind up being some path through here, and that path would either hit a dead end, and then we'd have to step back, or it would wind up getting to the finish. That whole point of it, if it runs into a dead end, it has to step back. That actually gives the name to the approach of doing this with recursion. And if you do this with recursion, it is commonly referred to as backtracking. And so this is one of the algorithmic techniques for searching a solution space like this, where you try a path as far as you can go. As soon as it goes wrong, you take a step back and you try a different route. And once that goes wrong, you step back until you can try another route. And you keep doing this, and so it does a depth-first traversal of the tree for the solution space, going all the way down and then stepping back up, and then all the way down, stepping back up, and all the way down, stepping back up. And it combines the results to find you the one that was optimal for what you were looking for. In the case of the maze, we're often looking for the length of the shortest path, or for the shortest path itself. Okay, and so this is not the only way to search through a solution space, though. This is what you happen to get if you do a recursive solution, but you don't have to write this recursively. Of course, the recursive solution is inherently using a stack. It's using the call stack. The function call here remembers where it is, so when you push this call onto the stack, that is still there, remembering that we need to go this way, and so when it pops back off, it goes in the opposite direction. If you have something where the tree goes too deep for your call stack, you can implement this using a while loop, and you can do something like stack.push of the initial case, and then while stack non-empty. I'm writing this in pseudocode. We make some variable, I'll call it n equals stack.pop, and then I would run through and stack.push n's children. Then do whatever processing it was that I needed to do to check to see if this were the if I had gotten to a solution. And so Because this is using a stack and the objects come off in a LIFO ordering, so that the last thing in is the first thing out, it would wind up going down to a child and going to a child, going to a child before it went to the siblings. What if instead of being a stack, though, we change this to a queue? And okay, change pushes and pops to whatever term you like for adding things and removing things on queues. Then what happens? Okay, well, this same type of algorithm is no longer going depth first. Instead, this would be a breadth first traversal. And that's something we don't refer to as backtracking in the algorithm's terminology. This is called branch and bound. And you can make an argument that this maze problem here would actually be done much better in branch and bound than it is through backtracking. And the reason is that because this goes across each row, you use branch and bound in situations where what you're looking for is going to be high up in the tree. In the case of the maze, the first node, however deep it is, the first node that gets to the finish, that's your answer. That's the one that you wanted. And so you don't have to keep going down the tree. There could be paths that are much longer than that, but you don't need to search them because you really don't care. The problem with branch and bound, so with the backtracking, when you do this recursively, you only have to manually implement a stack if you're actually going to overflow your call stack. And it would be extremely weird to have a tree whose depth was so large that you overflowed a heap-based stack. However, with branch and bound, let's just consider the case of a tree that grows that's completely binary, like this. Now, of course, that's not quite the case for this maze, but there are lots of problems where the tree that you're searching for for your solution space would be a binary tree. So at the first level, we have one node, and our queue has one thing on it. After we process this one, it then has two. After we've processed all of those, the next level has 4, and then 8, and then 16. And so the number of values that are stored in here is going to grow as 2 to the n. Oh, and does that button not? Oh, that's just an increased font size. Bummer. Don't have an easy way of changing that to a superscript, and I'm not going to bother for the video. So this grows as 2 to the n, and that exponential growth means that you're not going to be able to push this very far down. By the time you go down 30 levels, you will have on the order of 1 billion elements that are in this queue. So you're using several gigs of memory, depending upon exactly what it is that you're pushing into the queue. And that's going to strain most modern computers. So for this maze, which is a 12 by 12 maze, and it has the shortest path that is probably on the order, it's less than 30, but it's probably getting pretty close to 30. I haven't actually counted up for this particular maze. This would actually, if this were a complete binary tree, it would push the limits of branch and bound. Because there are so many blocks here that you wouldn't follow, you could probably get away with doing a branch and bound on this and not have it overflow. But that is the thing you have to worry about with branch and bound. So for this video, we introduced the concept of having your solution space represented as a tree, and then talking about how we do a traversal on the tree. We talked about doing the backtracking, which is basically a recursive solution where we go depth first through the tree, and then branch and bound, where we do a breadth first traversal of the tree. We're going to come back in the next video and talk about certain situations where we don't need to explore the entire tree and what we can